Hi guys, welcome back to another video. Today we're going to be looking at enthalpy changes, and what this means, we've seen this before, ΔH. This is all about heat, how heat changes in a chemical reaction. To start off with, this lovely meme. I found this on the chemistry memes subreddit. It exists. So here we can see 3D10. And he's ready to take his place after 3p6. But then 4s2 stops him. As we all know, 4s2 goes before 3d10 in our electron orbital order. What a funny meme. 10 out of 10. So, going back to ΔH, we learned this last year. We saw exothermic and endothermic reactions. I'll give you a couple seconds to think about what type of reaction is this. We start off our reactants with high amounts of energy. They have to cross over a low activation energy barrier, and then they're going to go down to the products, which have a lower amount of energy. Because we started off high energy, and then we went to low energy, this energy had to go somewhere. Where did it go? It went out into the surroundings. Because energy went out into the surroundings got hotter. It's an exothermic reaction. As we can see here, our arrow for ΔH, which is the change in heat energy, we call this enthalpy. The change in heat energy decreased, so ΔH is negative. In exothermic reactions, ΔH is negative, and in endothermic reactions, ΔH is positive. Okay. We're now going to look at ΔH in regard to phase changes. A phase change is when we change from one state to another. For example, going from a solid to a liquid to a gas, or even from a solid to a gas. These phase changes involve breaking intermolecular forces, the same forces we looked at in a previous video, and we're going to break these forces with energy. So, down the bottom here, you see we have energy input. This is how much energy we're putting into our system in the form of heat. And normally, we're very used to this blue line. As we put in more energy, the temperature increases. This is familiar to us. What's unfamiliar are these red stationary points. What's happening? We're putting in energy, but the temperature is not increasing. That is because the energy we're putting in does not go into heating it up. It goes into breaking forces. Breaking intermolecular forces holding, in this case, the solid together. So we have the solid chilling together, all the particles are vibing, they're close together, being held together by intermolecular forces. If I want to make into a liquid, I have to break some of these attractive forces. I'm breaking these forces with energy that I'm putting in. It's the same thing when going from a liquid to a gas. When you have a boiling pot of water on the stove and you keep turning the heat up, the liquid's not going to get any hotter. It's not going to make your pasta cook faster. All that's happening is you're going to make it boil a bit quicker and turn into more and more steam or water vapor in the form of gas. So, the first thing we have to look at is ΔH fusion. This is called the enthalpy of fusion. This is the energy needed to convert 1 mole of solid into 1 mole of liquid under standard conditions. This standard conditions just means standard temperature and pressure. Standard pressure is 1 atmosphere, which is just what we feel on the surface of Earth, and standard temperature tends to be around 25 degrees, room temperature. So, for example, if we take solid ice, so this is solid H2O, and we want to turn it into liquid ice, or water, this is going to require some energy. How much energy? Not much. 6 kilojoules per mole. This is pitiful amounts of energy. So not much energy is needed, and because it's at standard temperature, it's at 25 degrees, it'll happen very easily. So not much energy at all is needed to turn this ice, 1 mole of ice, into 1 mole of liquid. This is called delta ΔH fusion, the enthalpy of fusion. If you guys can pause the video now, copy down these notes into your books, then we can continue. So what we just saw was the ΔH of fusion, and this is going from a solid to a liquid. So this is this phase change here. The next phase change we're going to look at is this one, vaporization, going from a liquid to a gas. So ΔH of vaporization is the enthalpy of vaporization. This is the energy needed to convert 1 mole of liquid to 1 mole of gas at its boiling point under standard conditions. What does that look like? This means turning from a liquid to a gas, it's going to take this much energy. A little bit confusing, but I think we can all understand this. Alright, if you can pause the video again and take down the second set of notes, that'd be fantastic. Cool, and this was this one here. The very next one we're looking at is going from a solid to a gas all the way up here. So we're skipping both steps. We're skipping the liquid phase. This happens with commonly dry ice. Dry ice goes from a gas to a solid and solid to a gas. At Earth pressure, air pressure, CO2 cannot exist as a liquid state. It goes straight from a solid to a gas. Dry ice to carbon dioxide. And this is called the ΔH of sublimation. The energy needed to convert 1 mole of solid into 1 mole of gas under standard conditions. Another molecule that undergoes sublimation is iodine. Iodine can turn from a solid to a gas, skipping the liquid phase. And to do this, it requires energy. How much energy it requires? It requires 62.4 kilojoules for every mole of iodine you want to turn from a solid to a gas. This is a video showing this happening. It's a very cool experiment. You get lovely crystals of iodine forming on your flask. I will put this also in the Google Classroom for you to watch. And if we can pause the video now and take down the third set of notes, it'd be fantastic. So, summary of today's video. We've looked at the ΔH of fusion, which is going from a solid to a liquid, ΔH of vaporization, going from a liquid to a gas, and ΔH of sublimation, going from a solid to a gas. In all of these cases, our value, the value for ΔH, was greater than 0. Because it's greater than 0, it requires energy. This energy comes from the environment around it. It's absorbing the energy, which makes the surroundings feel cold. Therefore, it is endothermic. Endothermic means it feels cold. It feels cold because our reaction is taking in energy from the surroundings. These are all physical changes, and we're going to be looking at some chemical changes next time. The chemical changes, just in case you're curious, is all about entropy. New word. We're going to learn about this next week, either in class or online. Who knows what's going to happen with lockdown? We can wait and see. There's a Google Classroom task that'll be online for you to do. It's going to be looking at a couple of these questions, but it's mostly about intermolecular forces from the last video. All right, thank you for watching.